ಅಣ್ಣಗಳಿರೆಲ್ಲ ಕೇಳಿರಯ್ಯ ಮಣ್ಣಿಂದ ಕಾಯ ಮಣ್ಣಿಂದ ಮಣ್ಣಿಂದ ಕಾಯ ಮಣ್ಣಿಂದ.
Welcome you all to the second lecture, that is module 1.2 in the module second chapter, first module second chapter, that is bearing capacity. Here we are going to discuss about introduction, important definitions, modes of shear failure, Terjigis bearing capacity equation, that is a theory, and after that we are going to study about Indian standard bearing capacity equation, plate load test, standard penetration test, cone penetration test, and some problems we are going to study. These problems I will explain in the next class. Then what is bearing capacity? Bearing capacity means it is the ability of a soil to withstand the load coming from the superstructure. Why we are going to study this one? Because the foundation, which is very important part of the structure which transmits the load which is coming from the superstructure to the ground. Okay, when you are transferring the load coming from superstructure to the ground, then the ground should resist that one, or otherwise the load should be transferred to the ground without any failure or without any settlement. Then the soil is considered as a good soil. Therefore that is called as a bearing capacity, means ability of a soil to withstand the load. Okay, here some important terms are there. Here the foundation. What is this foundation? Foundation, we have a two types of structures. Whenever you build whatever the structure that has a two types: superstructure, which we can see above the ground level, and substructure, which we cannot see, that will be below the ground level. Therefore the below the ground level whatever that is there, that is called as foundation. But technically this is the lowest part of the structure which is in contact with the soil and which transmits the load to ground. Okay, which is called as substructure of the building. Now what is foundation soil or bed? Soil, everywhere soil is there, but the foundation soil is the soil which is responsible to transmit the load coming from superstructure to the ground. And footing means what? Footing is a part of the foundation. Foundation is a massive structure, and a part of the footing, that is your for one column or two column, you will give some foundation, that is called as a footing. Bearing capacity. Now see, these terms are very important. Bearing capacity, gross bearing capacity, net bearing capacity, ultimate bearing capacity, net ultimate bearing capacity, net safe bearing capacity, safe bearing capacity, settlement pressure, allowable pressure. These all somewhat looks similar, but small differences are there in that we need to observe. Bearing capacity means what? Whatever the load which is coming on the soil, that divided by area of the footing. Here we are not making any standard specifications which load it is coming, which area we need to consider. That all specifications are not there, just it is a bearing capacity. Okay. Now coming to the gross bearing capacity, it is also of course load divided by area only, but here we are considering all the loads which is coming on the foundation, that is superstructure load, dead load of the footing or foundation, and backfill. Here any building which will be having some superstructure, and below that one you will put some foundation. This foundation also has some load, that is a dead load of the foundation, and after that you will put back some soil. The wherever the hollow portions will be there you will put some soil, that is called as a backfill. And all together this is a load divided by the area of the footing, that is called as gross bearing capacity. Gross it is because everything is there here. Now net bearing capacity means we are ignoring this backfill, means the same equation, load coming from superstructure, dead load only, divided by area of the footing. Then what you are ignoring? You are ignoring backfill divided by area. That backfill by area we will consider it as a gamma into D. Therefore net bearing pressure, net bearing capacity equal to Q, that is a gross bearing capacity, minus gamma D. Ultimate bearing capacity. Now see, ultimate means what it is? It is the maximum bearing capacity that can be applied or that can be resisted by the soil without a shear failure. Okay, the maximum pressure which a foundation withstands without considering shear failure. This word shear failure is very important. This is the first criteria to meet. We are going to build the foundations, and it is denoted by QU. Next, net ultimate bearing capacity. See, this is the ultimate bearing capacity, this is the net ultimate. Net means what? We need to deduct something which is not very useful for us. That is called as net, which is not required for us for the design. That is a net. Therefore, here we are considering this gamma D. Gamma D, if we remove from ultimate bearing capacity, then we will get a net ultimate bearing capacity. This will be more and this will be less. After that, we are applying some factor of safety. And why factor of safety is required? Because we estimated some strength of the soil, but the entire strength we cannot, whatever estimated, that much load we cannot apply, because some uncertainties will be there, some calamities will be there, natural calamities will be there, they all occur. Therefore we need to be very safer side. Therefore we need to underestimate the strength of the soil. That is your factor of safety. We are underestimating that QNU divided by F, you got net safe bearing capacity. Then this is a net and this is a grass, therefore this will be more and this will be less. Then how much more? This much. That is gamma D, we need to add back to QNS, then we will get a QS. And QS is QNU divided by F plus gamma D. QNS, this QNS, it is replaced with this equation gamma D. Then QS equal to QNU means what? This QNU we got from this equation, that is QU minus gamma D, that we have substituted here. This is not plus, this is minus. QU minus gamma D divided by F, and this is plus. This is plus gamma D. Please interchange this one. This is minus and this is plus. Next, coming to the other part of the foundation, that is a settlement. Settlement means what? This is not a bearing capacity, it is a settlement pressure. Means the maximum pressure at which the foundation should not exceed the permissible settlement. Here the permissible settlement is very interesting. We cannot avoid settlement in soil, because soil is a compressible, voids will be there. You apply some load and obviously it will settle down. Okay, we cannot avoid a complete settlement. Therefore there will be a settlement, but we will call that as a permissible settlement. We will have some value, that permissible settlement, for that we will design. If it exceeds more than that, then the structure will damage. Okay. Therefore the maximum pressure at which foundation settles will not settle more than permissible settlement, that is called as settlement pressure. Now allowable, then how much we need to allow? Whether safe bearing capacity, which is taking care of shear stress, and settlement pressure, which is taking care of settlement, which one you need to allow for the ground? This is very important question. Now allowable bearing pressure, before answering this allowable pressure, we need to consider why we are building a foundation. First thing is to transfer the load from super to the substructure, and the second one is very important, to meet two criteria. One is below the foundation, that foundation soil should not fail in shear, first criteria. Second criteria is settlement should not be more than permissible, second criteria. To meet these two criteria, we are providing foundation. Then when we have a value of bearing capacity that will take care of shear, and settlement pressure that will take care of settlement, when we have a both value, the minimum of these two we need to take and we need to allow on the ground. That is called as allowable bearing capacity. You just think yourself, why we considered least of these two, why not maximum of these two? Okay, you need to think yourself and answer it. Okay, these are very important terms in bearing capacity. coming to the modes of shear failure. Below the soil, below the foundation, there is a soil. This is studied by Carl Terjgi, who is the father of geotechnical engineering. He says that the soil below the foundation, which fails of course, but it has some standard patterns. It will fail in some standard patterns. Those patterns are divided into three different modes. That is a general shear failure, local shear failure, punching shear failure. These three are patterns. If the soil is very strong, very good, very high dense, then it will fail in general shear failure. If the soil is somewhat medium, weak, and not that higher, not that strong and all, then that is called as a local shear failure. If the soil is very weak and it is just like a powder and uniform size, there are many voids, clay in nature, less density, then it will be punching shear failure. The soil fail in punching shear. Therefore, the modes of shear failure says that the soil below the foundation will fail in three different modes. Okay, the first one is, you can see here, this is a foundation here, and initially this dotted lines are there, that much ground was there, and as the force increases, this will start penetrating inside, and when it penetrates here, this is a very hard soil, very intact soil. Therefore, this much volume it is penetrated means that much volume you will absorb in a bulging. Therefore, when you see a soil bulging at the top, then you can think that the soil is failing below the foundation in general shear condition. Okay, these all points are here. The very important points are here, that is the SPT n value. N value means what? You are going to penetrate something into the soil by giving some number of blows. If it takes more number of blows, that is more than 30 number of blows, means what? It is very strong soil, because it is not penetrating with a less number of blows, it is taking more number of blows, it is a very strong soil. Then another indication is, if the phi value is more than 36, it is very strong soil and very dense soil. The density you can measure it from relative density equation. That relative density, if it is more than 70%, is very high. Then very good soil, if it is there, then as you penetrate the foundation, it will bulge here. By seeing the bulging, you can say it is a general shear failure. Then I will explain the punching shear failure first. Second, punching shear failure means what? The soil is very weak and it is a clay in nature, powdered in nature, or saturated with water content. Clay and saturated with water content. There are many voids are there. Density is very less. Therefore, it is considered as a weak. And when it penetrates here, see, this is penetrated this much, but there is no bulging. It went inside without making any changes in the ground surface. Therefore, we can say this is a very weak soil. Okay, it is not resisting the load applied. Therefore, it is a very weak soil. This such type, if you are observing, then you need to avoid such soil, or you need to make some modification to get a good strength to the soil. And next, coming to this local shear failure, these properties falls between general shear failure and punching shear failure. All the properties means it is not too strong like a general shear failure, it is not too weak like a punching shear failure. In between the property falls, that is your local shear failure. Okay, the graph also you can see here, the pressure is there here, settlement is there here. The first one, A, general shear failure. See, take this point, at this point it is taking this much of pressure, but settlement is very less. And same point will come here, then it gone through this much of settlement, but the pressure is the same way. And coming to this one, it will come somewhere here for the same pressure, but settlement is large. Okay, means this indicates very weak, medium, and very dense. Okay, these, by seeing the graph also you can classify the modes of failure. Next, Terziki's bearing capacity theory. Terziki's bearing capacity theory, here we are going to study assumptions made by Terziki and concepts of Terziki and derivation of that equation, okay, and some factors which affects the bearing capacity and all. Now coming to the Terziki's equation, assumptions here we make before derivation, that is soil is homogeneous and isotropic. Homogeneous means in all the point the properties are same. Isotropic means at a particular point in all the direction the properties are same. Then shear strength of the soil is represented by Morse Coulomb criteria. Morse Coulomb criteria means the horizontal sigma and vertical shear stress we are going to consider, and that is drawn. The footing is of a strip footing type and rough base. It is essentially two-dimensional plane strain problem. Okay, here he is considering strip footing. He is not considering rectangular, circular, or square footing. He is considering strip footing. Strip means what? It will be somewhat very long in length and very small breadth will be there. Then long in length, long means how much? If the breadth is b and if it is length is more than 5 times of the b, then we can call that is a strip footing. Okay, and he assumed that strip footing for the study purpose. Then here he considered two-dimensional plane. Why? Because he considered breadth as a b, but perpendicular to the board or perpendicular to the paper, it is considered as 1 meter, unit meter. Okay, therefore it is considered two-dimensional plane strain problem. Then the third one is elastic zone at straight boundaries inclined at an angle theta phi to the horizontal. This is very important. I'll show in the figure. Here this is a figure. Terziki assumes the general shear failure. Therefore, in the general shear failure, you are going to see some failure patterns here. And here, this is called as elastic zone. And this, this is called as elastic zone. This elastic zone means this wedge is there, no? This triangular wedge. This is called as elastic zone. And this elastic zone is making an angle phi with respect to horizontal. This is assumed in the theory. Then failure zone is not extended above and beyond the base of the footing. Okay, shear resistance of the soil above the base of the footing is neglected. Now see, actually in general shear failure we should observe some bulging here. Okay, but in assumptions in general shear failure we are assuming some bulging here. But here we are ignoring. Why? Because we put some backfill here and we ignore that bulging activity, or we assumed in that way. And the second thing is that the properties of this soil is not considered at all. The properties of these soils are studied and the properties of these soils are ignored. That's not required for us. Then method of superposition is valid. Method of superposition means you can make into small parts and you can study individually and collect the information at the end. Sum up all the information at the end, that is possible in the test. Then the passive pressure force has the three components. Passive pressure means what? In lateral earth pressure chapter we study earth pressure, that is active, passive and at rest earth pressure. Passive earth pressure means retaining wall pushes the soil, and active earth pressure means what? Soil pushes the wall. But here the foundation is pushing the soil, therefore we consider passive earth pressure concept here. That is assumed in the bearing capacity. Effect of water table is neglected, and below this one, below the ground level, wherever that water table may be, but to derive the equation we are neglecting. Then if water table is there, then what we need to do? We need to apply some corrections and we need to discuss. Then concepts. In this concept, as he assumed that this is general shear failure, we come to the above figure. The concept says that this zone is a failure zone. Below the foundation, this zone is a failure zone. Here it is divided into 5 zones. This is one zone. This is a triangular portion. It is a one zone, and this is considered as a part of the foundation, which is very rigid. Okay, and this is a second zone. Okay, 2 zones of second here, and this is called as a linear shear failure. Radial shear failure zone. This is considered as a center point, and from here the radial strips will come that is radial shear zones, and this is linear shear failure. Here parallel strips we will consider when it fails. Therefore this is radial linear shear failure, radial shear failure, and this is part of the foundation. This is a rigid. Okay. For these two, plastic equilibrium applies, and for this one, elastic equilibrium theory applies. These are assumptions. These are concepts. Now coming to the derivation. Now we will study derivation of bearing capacity equation by Terji. See this figure, this is very important figure, and here a foundation is there, and the breadth of the foundation is B, and Q is the load coming from the superstructure which is acting on the foundation. This triangular portion is not a concrete, it is a soil. Okay, the concrete is only this much. Below that one we got a triangular portion. This triangular portion is based on the general shear failure assumption, but this acts as a part of the foundation. Therefore when it penetrates here, this soil will not fail at all. Then the failure soil will be here and there. Therefore to this foundation, when I consider this foundation, then I have to consider this triangular portion also a foundation. Then what is the angle of this triangular side? This side of this triangle, that is assumed it is a phi value, and here this is a 45 minus phi by 2. Okay, based on passive earth pressure concept, and here the whatever the surcharge it is acting, that surcharge load is considered as gamma into D. Now on this foundation there are 4 types of pressures acting. The first one is superstructure, that is a Q load which is acting on the foundation, and dead load of the foundation which is again acting downwards. And let us consider this Q includes superstructure and foundation dead load. Then we have another load here, this triangular portion, it is assumed based on general shear failure. Therefore we need to consider the dead load of the triangular portion, but it is made up of soil, that also we need to consider. And one load which is coming from the superstructure, second load which is coming down by the wedge of the soil, 2 loads are coming downwards, and third one is which is going upward, that is passive earth pressure. Passive earth pressure which is a resistance to the foundation, that is going upward direction, vertically upward. And there is one parallel to this one, you can see here, parallel to the triangular side, that is your cohesive nature. Like that there are 4 type of forces acting on the foundation soil, that is listed here. The downward forces are QU into B into 1. B into 1 is what? Let us consider bearing capacity is a QU, small QU, and B into 1 is the area, because perpendicular to the board is 1 meter. In assumption it is assumed strip foundation. Okay, the area is B into 1, and the QU is the bearing capacity, that is QU into B into 1, that is you are acting downwards. And the second one is, as I said, that the weight of the wedge. Then the weight of the wedge means we should know the volume of the wedge. Volume of the wedge, before knowing that one, perpendicular to the paper is 1 meter. Then what is the area of this one? Area into perpendicular distance, we will get a volume. Okay, then let us consider this as a X and this is a B, then we will get a area of this one. Okay, then we don't know X here, therefore we need to express this X in terms of B. We will consider it as a phi, and this is the tan phi equal to X by B by 2. This is a small portion is a B by 2 from here to here, and this is X divided by B by 2. Then X equal to B by 2 tan phi. Then you got a X value. Then what is the area of this one? Half into B into X, that is the area. Then what is the volume? Into 1. Therefore volume into density is your weight, that is half into X into B into 1 into gamma. Okay, then here in place of X we are substituting B by 2 tan phi B into gamma. Then here we are getting 1/4, this is 2 into 2 1/4, this gamma and B square tan phi. This is your weight of the wedge which is coming down. Two forces are over. Then the third one is upward forces, that is the resultant passive pressure PP on each surfaces, that is dB and dA. There is dB and dA. See, this is a D and this is the A, dB and dA. Okay, this is your two passive pressures which are acting on dB and dA, and the vertical component of cohesion acting along the length of dB and dA. Same here in this surface, dA and dB, here some cohesive parallel to the surface cohesive stress is acting. Then what is the area of this one? It is dB into perpendicular to board 1 meter, dB into 1, and this is dA into 1. This is the area. Okay, and these two are upward forces. Okay, now considering here Q is it is straight downward, and this weight of the wedge is also downward, PP is upward, all are in one line, but the CC is there. Now the CC is not in vertical direction, it is inclined with some angle, therefore we need to resolve this force to the vertical. Okay, therefore that resolved forces I can call it as, I can consider this the length of dB first I will calculate, b by 2 cos phi, and the critical component will be equal to C, vertical component will be equal to, means this inclination I need to resolve into this way, means I should know some value here. This value is called as cos theta by using this value is called as sin theta. By using that one we are going to make it, that is b by 2 C tan phi. Then for equilibrium condition, downward force equal to upward force, that is write all the expressions which you calculated here, that is q into b and 1/4 q gamma b square tan phi, and this pp 2 times of pp, and this b by 2 C tan phi, that write everything here. Then take this QUB this side and send everything other side. Okay, then we will make another assumptions here. In the assumptions only it is listed here, you can see the passive earth approach has a 3 components, that is PPC, PPQ and PP gamma. Okay, PPC means the passive earth pressure because of cohesion, passive earth pressure because of surcharge, passive earth pressure because of shear zone. Okay, these all PPs are there, therefore we will consider the total PP equal to PPC, PP gamma and PPQ. These three we will substitute in this equation, then we will get this expression. Here this is the gamma, this is related to gamma, and here also some gamma is there, therefore this term and this term we will put in one bracket, and this belongs to C cohesion and this belongs to cohesion, that we will put in one bracket, and this surcharge property that we will put it separately. Now we got a 3 brackets, this. It becomes very difficult to calculate PPQ, PPC, PP gamma. Therefore, Terjigi suggested some substitutions. That is, this entire bracket can be substituted in this name, that is B into half gamma B n gamma, and this entire bracket can be substituted as B into C into NC, and this entire bracket, this one term can be replaced as B into gamma D into NQ. Here NQ, NC, N gamma are some bearing capacity factors. Terjigi will give you one table. In that table you are going to see 5 value and you are going to analyze. Then you are going to get a QU equal to CNC, because this here BC into CNC is there, this B here and B everywhere is there, that B will get cancels. Then the ultimate equation you will get CNC plus gamma D NQ plus 0.5 gamma B N gamma. Now this is ultimate bearing capacity. Net bearing capacity as per the earlier definitions, QU minus gamma D. Safe bearing capacity, QU minus gamma D by F plus gamma D. Here NC, NQ, N gamma depends on phi value. Okay. If a phi value equal to 0 means it indicates a non-cohesive soil, pure cohesive soil, then we can assume NC equal to 5.7, NQ equal to 1 and N gamma equal to 0. Okay, according to Terjigi. Then our equation becomes QU equal to 5.7 C and gamma D. Now As it is said in the general shear failure, if phi value is greater than 36, that is considered a general shear failure. If the phi value is less than 28 degree, then it is called as local shear failure. Then this is local shear failure, but this derivation is done for general shear failure. Then what all modification we need to do for local shear failure? Terji suggested that in place of C, you need to substitute C dash, and in place of phi, you need to substitute phi dash. Then the entire equation will be as it is. Then the C dash will be equal to 2/3 of C, and phi dash will be equal to tan inverse 2/3 of tan phi. And the same thing you need to substitute here. Then the bearing capacity ratios becomes, factors becomes NC dash, NQ dash, and N gamma dash. As it is observed that in assumptions, this derivation is done for strip footing. Okay. If in the practical, in the field, if we have a circular footing, square footing, rectangular footing, then we need to modify that equation. That is, for circular footing, 1.3 we are multiplying for this term, and 1 to this term, 0.6 to this term. Then the equation becomes 1.3 CNC, 1 into gamma d n q, then 0.6 into 0.5 into b into n gamma into gamma. And for square footing, if we have the same thing, 1.3 CNC, 1 into gamma d n q, 0.8 into 0.5 gamma b n gamma. Then if we have a rectangular footing, then 1 plus 0.3 b by l into CNC, 1 into gamma d n q, 1 minus 0.2 b by l, 0.5 gamma b n gamma. These factors you need to multiply. They are called as shape factors. These shape factors are to be multiplied to the main equation, then get the ultimate bearing capacity equation. Now, in the assumptions, it is assumed that the bearing capacity, if it is a water table is in the assumption, it is assumed that water table is ignored. If water table appears too near to the foundation, then what we need to do? Therefore, there are some guidelines here that we need to apply. That is, your equation will be modified like this is your original equation. This equation modified as CNC as it is plus gamma d n gamma. Here one term will come RW1, and here 0.5 gamma b n gamma, and here another term come RW2. This RW1 and RW2 are called as reduction factor for water table. Now see, then how to calculate this RW1 and RW2? RW1 is 0.5 1 plus ZW1 by D. RW2 is 0.5 1 plus ZW2 by D. B. Then what is this W1 and ZW1 and ZW2? Coming to here, this entire soil below the foundation or near to the foundation will divide into two parts. The one is, we'll put one dotted line here. This is the first zone and this is the second zone. And this first zone, the depth is D, and the below this second zone, the depth is this B. This is the depth B and this is the depth D. Therefore, wherever gamma is multiplied to this D, that is called as a gamma D, that we will observe in the second term, gamma D. And whenever comes to the second zone, this gamma is multiplied to this B, and we will have a term gamma into B. Okay, therefore RW2 is multiplied to the second term. It means that RW2 belongs to the second term, second zone, and first term will be multiplied. This term is multiplied with RW1, means RW1 belongs to this zone. Okay, therefore wherever the RW1 is there, ZW1 will appear. Wherever RW2 is there, ZW2 will appear. Then ZW1 will be measured from the ground level, and it will go up to distance D, means its limit is from here to here only, and ZW2 will be from here to here only. These ZW1 and RW2 you need to measure based on water table. Say for example, if water table is here, then ZW1 is that much. That ZW1 value substitute here, will get RW1 and multiply to the original equation. Then if water table is here, then you need to take ZW2, that substitute here in RW2, then substitute that RW2 into the main equation. Then coming to here gamma is there and here also gamma is there. Then which gamma we need to take? Whether the gamma belongs to this zone or this zone. If the soil is completely dry, then we have only one gamma, that both gamma will be same. That the second term gamma and third term gamma both will be same. If the soil, this soil is saturated and this is a dry, then the gamma corresponding to this means what? Gamma which is multiplied to B, and gamma which is corresponding to this means gamma which is multiplied to D. This is this. Okay, based on that they will change. We will call this as a gamma 1 and this is a gamma 2. Then those definitions are given here. Okay, then effect of eccentric foundation. See here again the bearing capacity is calculated based on the concentric loads which is acting on the ground. If any eccentric load is acting on the ground, then it changes its meaning. See here, this is what concentric figure is not shown here. Here some load is applied here, therefore some stress is more here and some stress is less here. A uniformly changing stress is there, and here the load is strike to the left side and you are going to see some eccentricity. This is called as one-way eccentricity and this is a two-way eccentricity, because in x direction and y direction, in both the direction this point is shifted, but here it is shifted in one direction. Okay, this is one-way shear eccentricity and this is a two-way eccentricity. Here the everything whatever we studied about the equation, everything will be same, but the difference here what we observe here is the B value. Okay, this B becomes modified breadth. Modified breadth will be B minus 2 into E. E is your eccentricity. Okay, E is your eccentricity. If we have one-way eccentricity, then only E will come, that is B minus 2E. Then L will be lengthwise, you don't have any eccentricity, therefore L will be L only. Therefore B becomes B dash equal to B minus 2E. And if you have two-way eccentricity, that is B dash equal to B minus 2E, L dash equal to L minus 2E. Then this is your B dash and L dash, you got a different dimensions of foundation. Then this, by using this different dimensions, you need to calculate the area, and this area you need to substitute into your equation. Where is that equation? Here, area of the footing, there you need to substitute those B dash and L dash. Okay, that is your correction for eccentricity. Okay, now Indian standard bearing capacity equation. Indian standard bearing capacity, it is borrowed from Terzi's bearing capacity equation only. Small modifications we made it based on our ground condition, Indian soil conditions. We made small modification. That is CNC is already there, but we have introduced SC, DC, IC. Gamma D NQ according to Terzi, it is already there here. There also, but here also it is there. But we have introduced SQ, DQ, IQ. And 0.5 B gamma B N gamma. It is already introduced by Terzi, but Indians we introduced S gamma, D gamma, I gamma. Then the equation becomes this much bigger. Here S, D, I indicates that S indicates shape factor, that is SC, SQ and S gamma are shape factor, and DC, DQ, D gamma are depth factor, IC, IQ, I gamma are inclination factors. And these values are empirical, means what? By doing so many experiments they have concluded those values, and that is given here. Okay, you can go through them. These are the values. Next, if we are unable to determine the bearing capacity of the soil in the laboratory, What I mean is, the soil you bring to the laboratory and you determine some values or some properties like gamma, shear stress, shear strength, that is C and phi, and some other properties you will determine. Based on that, if you are not able to determine bearing capacity, then what you need to do? You need to conduct in situ test into the field. In situ tests somewhat give you a very good and accurate and practical result. Therefore, we prefer a best in situ test to determine the bearing capacity and settlement is plate load test. Okay. This plate load test, you can see here, we will dig a pit here. The width of the pit is called as B pit, and this B pit will be 5 times of B plate. Here one plate will be used because this is a plate load test. Therefore one plate will be used. That plate width will be B plate, and this B pit will be 5 times of B plate. And on the plate, this plate is made up of steel, mild steel, and below some grooves will be made, and the dimension of this plate will be 300 mm to 750 mm, and the thickness is 25 mm. And above that one we will put 2 or 3 diagonals in 120 degree each, or otherwise 90 degree each, 180 degree each. Okay, means opposite to opposite we will put 2 dial gauges, and whatever the settlements recorded in each dial gauges are written, and average of that one is considered as a settlement of the plate. And above that we will put some hydraulic jog because we need to push it down. To push we are using some hydraulic jog. Okay, then when it pushes it downwards, someone should be there to resist it upward. Therefore we will put one steel girder here. Above that one we will put large many number of sandbags. These sandbags acts as a resistance to the load which is pushed by the hydraulic jog, and these sandbags can be rested on a masonry wall. Okay, this is all about the arrangement of plate load test, and whatever the arrangement I have said, that all arrangement is written in these points. Now coming to load application, here we need to go on applying the load. The rate of load, it is depends on the type of soil and a plate you are using, that you are going to apply, and every time settlement is recorded, and those settlement and the load applied and the settlement, okay, these two are drawn in a graph. That graph is shown here. This is the pressure and settlement. Here the whatever the load you have applied on the plate load, that load pressure will be written here and the settlement will be recorded here. From this you will come to know what is from this you will come to know the soil below the foundation, or the soil which is tested, whether it is in general shear failure condition, local shear failure condition, or punching shear failure condition. Okay, here you can see a sharp edge is there and it is coming and it is going backward. Then the ultimate bearing capacity you can measure it this way, and here this has a two types of different slopes. One slope is here and one slope is here. You draw one line here and one line here. Wherever they intersect here, that is called as ultimate pressure. For punching shear failure, this considered as a ultimate pressure. Okay, and corresponding settlements can be measured here. Okay, this is about plate load test, and advantages and disadvantages you can go through them. Coming to the very important second in situ test is a standard penetration test. Standard penetration test means here we will be having some tripod. It is very bigger in size, and tripod we are going to put. Then this tripod is connected with some hammer. This hammer will be weighing 65 kg, and this hammer will be having some guided shell here, guided tool here, and one sampler will be there. That sampler, in the first chapter I have explained, that is the thin wall sampler, that is split spoon sampler. Split spoon sampler means what? Here the screws arrangement will be made. When it collects the soil sample inside, we can split the mold into two halves, then we can get the soil sample. That is called as a split spoon sampler. Here we are going to penetrate this split spoon sampler into the soil. How to penetrate? We will give some free blows. Means we will lift this hammer and we will drop it by gravity, and lift the hammer and drop it on the drop it by gravity on this sampler. Then this dropping height will be 750 mm, and for every drop this will go inside. Okay, now we need to count number of blows required to penetrate this sampler into the soil for about 300 mm. Okay, and in between if you want to take a rest, because 300 mm penetration requires many number of blows, therefore if you want you can divide this 300 mm into 150 mm 150 mm, two slots. Okay, therefore the definition become like this: number of blows required to penetrate this split spoon sampler by a 65 mm 65 kg hammer at a height of 750 mm for a depth of 150 mm plus 150 mm 300 mm is called as number of blows, that is standard penetration n value. They are called as standard penetration n value. All specifications whatever I mentioned, that is listed here. This is advantage and disadvantage. Cone penetration test. This is a cone penetration test, means here we are not giving number of blows, here we are putting it inside, we are pressing this one cone inside the ground. There will be one vehicle and inside every arrangement will be there, and below that we will put some rod and we will apply some hydraulic pressure, and that by using that hydraulic jack we are going to push it. Then the resistance offered to the cone will be recorded and that graph will be drawn. Okay, based on the resistance resisted by the cone, we are going to check the density, we are going to decide the density, bearing capacity and some other properties. Okay, cone penetration test can either be static cone penetration or dynamic cone penetration. Static cone penetration means what? Some one load we are going to put it and we will allow it, and dynamic load penetration means time to time we are going to change the load which is applied on the cone. Continuous record of penetration resistance with depth is achieved. Every time when it penetrates inside, then it will resist the soil. Soil will resist it. Therefore, that is recorded. Consists of 36 mm diameter, that is a sampler, and 36 mm diameter consists of a cone of 36 mm diameter, and cone vertex will be 60 degree. Cone is carried at the lower and steel end of the steel rod that passes through steel tube 36 mm diameter. Okay, which is already explained here. The same way you are going to collect it. Then the advantages and disadvantages you can go through. Problems we will see in the next class. Thank you.